Okay, so there'll be slightly fewer pictures today. I apologize for that. But I want to tell you some, well, lots more things. Okay, so this is a picture of the upper half plane, and I'm sure everybody has their own personal relationship with the upper half plane. There are many ways to have a relationship with the upper half plane. But for a number theorist, for me, when I see this picture, I think about quadratic forms. So I want to tell you a little bit about quadratic forms, because they'll be useful in various ways later. And then that won't take the whole lecture, so then we'll start talking about Apollonian circle packings. Okay. So let's pick something less dramatic than red. Okay, so quadratic forms. All right, so this is sort of, I mean, number theory, in some sense, a large part of number theory is about solving polynomial equations in terms of integers or rational numbers or solutions from number fields. And you know, beyond linear, the first thing that you study and is quadratic forms, and they have all kinds of beautiful things happening. And for me, the upper half plane is sort of where a lot of these things are happening. So a quadratic form is just something like this. So I might call that f of xy. It's got a discriminant, same as for the polynomial. And for a number theorist, we'll often want these forms to have rational or even integer coefficients. So if they're rational coefficients, I can multiply up the denominators to make integer coefficients without changing the solution to the form. And so I'll often multiply up so that they have no common factor and they're integers. And then we'll call that a primitive integral binary quadratic form. So I guess I should say binary up here.
Can I say something stupid
Yep.
that helped me, like when I don't think about quadratic forms, but like the discriminant for me, like it helped me to think about dividing the whole thing by y squared and getting a polynomial in x over y.
Mm-hmm.
And that's why the discriminants were the same.
Yeah, and we're absolutely going to do that. So if I set y equals to 1, you get a quadratic polynomial. Same as if I set x equals to 1, in fact, right? And so that's going to be closely related to studying this form. But I want something homogeneous. I want sort of the symmetry here. Okay, so I'm also going to be interested in positive definite quadratic forms. So that means that it's going to take positive values unless you actually plug in x equals y equals 0. This is a homogeneous form, so really I want to think about it as living projectively. So I'm not going to plug in both the variables being 0, right? Okay. And so this was mentioned at some point earlier, that one of the natural things to do with a quadratic form is to act on it by SL2Z and think of it as not changing very much. So this is really just a change of variables. So what I want to do is, suppose I have, let's see, I'm going to pick different variables here. So suppose I've got some form which relates to another form where this m here is an element of SL2Z. So let's give it some entries. And what I'm going to do is I'm just going to precompose by m. So I'm going to apply m to the variables x, y. Okay, so that means quite literally alpha x plus beta y and gamma x plus delta y. Okay, so this is just a change of variables. It's a linear change of variables. You're still going to get a homogeneous quadratic form. And it's going to have lots of the same things that you might also be interested in about your form. So in particular, it'll take the same values. Okay? So this is called proper equivalence. You could also do GL2 equivalence if you want. And so that's why sometimes people are explicit. I will just worry about SL2. Okay. So if this is the case, then we'll call these guys properly equivalent, or just equivalent, and I'll write that. Okay. Okay. So now, as Jaidev said, you can think about the roots of this, and it's not really very different than thinking about the polynomial itself, but we're going to think about it sort of just as a projective version of that. So it might have some roots. And when we're in the positive definite case, then the roots will be a complex conjugate pair. Okay? And so if I call one of the roots zw, then the other one is just going to be the complex conjugate. And I'm thinking of these as living in P1. And by roots, I mean this. Okay. And you can really go back and forth between the roots and the form. So if you have the roots, you can write down the form. Because just like if you have the roots of a polynomial, you can write down the polynomial in terms of the norm and the trace, or the product and sum of the roots. So the same thing works here, just projectively. Okay, and it's always up to scaling, because I'm working in P1, right? And so my Z and W are only given up to scaling to begin with. But like I said, the quadratic form doesn't change very much when you just add a scaling factor. We can essentially ignore that. Okay, so all right. Okay, and so now we have this SL2 equivalence on forms, and so then that's going to give us an equivalence on the roots if we think about the form as being associated to the roots. And so let's just be explicit about that. So if I do an equivalence by M inverse, just to make things simpler here, I have to put an inverse somewhere to make this work, so I'm going to put it there. Then what happens is you basically apply M to the roots. Okay, you can see that from this right here, and its conjugate. So these guys are M applied to whatever your original roots were. Okay. So basically what I've done is I've set up this here to be PSL2. Oh, yeah. Okay, I'm going to switch to PSL2 instead of SL2 here because we're thinking about things projectively. It doesn't make any difference, right? This just means that I allow -1. So this sort of relationship between the roots and the form is PSL2Z equivariant. Okay, so the philosophy here is that we want to think of things the same if they're in the same PSL2Z orbit. And so we want to know what can I associate. So I've got roots, but they're changing under PSL2Z. I've got the form, but its coordinates are changing. What can I associate to this which is not changing, that is the same under a change of coordinates? And the answer to that is lattices. So we're going to think about these things as lattices. And that's probably, for many of you, the first thing you think of with PSL2Z, I imagine. So that's one way to think about why one might do this if you're starting with forms. Okay, and so what I'm going to do is I'm given a form and say it has some root. Then what I can do is I can define a lattice associated to that form as being generated by those two coordinates. So this is a rank 2 lattice inside the complex plane, and I'm going to take this up to homothety. Because my root is only given up to scaling, because I'm thinking of it projectively, I have to allow my lattice to be scaled as well. Okay? And then what we get, which is very nice, is that the action of SL2 is just change of basis, and so it doesn't change the actual lattice as a lattice. It just means you're going to ignore what the basis is. Okay. So as usual, we have to worry about orientation here. So we've got positive orientation or negative. I imagine this agrees with what you're familiar with. Hopefully I'm not doing it backwards or something. Okay, so this would be negative if we're going from Z to W. Okay, so if I'm listing my lattice, I'm not giving you a basis of the lattice, but I'm telling you an orientation of the lattice, which is like one bit of information about the basis that I might choose. And so in our case here, if I write it like this, one of either this guy, or if I use the other root, that one of those will be negatively oriented and one positive. Okay? So that means that even though I have two roots, I can sort of choose a way to pick one of them. Okay? All right, and so what we get is a very nice bijection. I guess I want to go down here to write it. So on the one hand, we've got quadratic forms. Okay, let me just write a Q. And so we've got all of the qualifiers here. So positive definite. And I'm going to put, here, maybe I'll write it in red. I could choose to say primitive integral. So the red is optional, okay? I can choose to put that in if I want. Up to equivalence. And I'm going to throw out the ones with discriminant 0. And I'm going to get a bijection between that and the set of lattices, so homothety classes. Of negatively oriented rank 2 Z lattices in C. Let me give it a name, Z. And then if I want primitive integral on the quadratic form side, then it turns out that what you're doing is you're requiring the ratio between alpha and beta, because of course alpha and beta are just up to homothety, so we can only talk about their ratio. This should be an algebraic number of degree 2. So what's happening is that when the number theorist wants to study this space, they're particularly interested in the red on both sides. We're interested in primitive integral quadratic forms. That's what's going to be useful for us for Apollonian packings and so on. And what that corresponds to on the lattice side is that you have a lattice which is really living in a particular number field of degree 2. Okay, so that's the fundamental bijection. I guess I should maybe say that, to be explicit here, our map, right, takes us to the lattice. And then, as you know, you can think of both of these situations as giving you a number, right? And this number then will be above the real line because of the orientation that I picked. And hopefully I picked the correct one for the way I wrote it. Okay? So I'm going to put my tau on the first entry. Yeah?
Can you remind what the alpha and beta is?
Remind which what?
Alpha, beta.
So I'm just giving it a name here when I say alpha, beta. So those are whatever's generating my lattice. So if I pick a basis, and then I take the ratio.
They're not Z and W?
Oh, yeah, well, so, okay. I guess maybe it makes more sense to write C and W here.
You picked right, because you put Z equals 1 and omega equals I, that's positively oriented.
Yeah, and I'm going to write tau Z plus 1 Z when I, yeah. There's always a danger. Okay, and so what this means is this is above the real line in the complex plane, so we're talking about the upper half plane, right? And so that's this picture here. And this picture here shows you the action of PSL2Z. So there's some generators S and T, T being translation by 1, and those are all the images of this gray shaded fundamental domain labeled by the words that will get you there. Okay? And so this is the space of rank 2 lattices, if you like. It's also the space of quadratic forms. Now, if you're a number theorist, you take this a little bit further, and you're very interested in this part here, which says that you're really living inside a number field of degree 2, and a lattice inside a number field of degree 2 can be interpreted as an ideal. And so you get the bijection. If you take this slightly farther, you get a bijection between quadratic forms and ideals of imaginary quadratic fields. Okay. Okay, and so let's see. So this is the notation I'll use for the upper half plane. And now we've got lattices. And I might say like C here to mean I'm not including the red. Okay, so I could also talk about maybe a Z as a subscript to indicate that I'm including the red in my bijection. Yeah.
Kind of a stupid question. So, like, you have your Z and W, but you could multiply Z and W by any real number. And
Yeah.
you also get another scaling the lattice.
Yeah.
But then you want to interpret it as an ideal and a number.
Yeah.
So
Yeah, so-
how do you scale it?
Yeah, so there's two different ways in number theory to define the ideal class group, for example. One way is to deal with just the integral ideals, which are literally subsets of the ring. The other is to think of things up to homothety and talk about fractional ideals, which allows you to just multiply and scale and think of that as a class of things, of which there will always be a representative, which is actually an honest-to-goodness ideal. So you can always scale it into the ring is the answer.
So could you set W equal to 1?
No, you have to, no, not always. So that might not get you an integer for the other, right? So Z over W, if it's not an integer, you're going to have to scale up by some denominator, and then it'll become two integers, Z and W, and then you've got an actual ideal. Yeah.
And you can scale by anything in C, not just on.
Yeah. Yeah, so there's rotation and scaling geometrically, yeah.
If I don't want to deal with coordinates C and W, we have that condition in double brackets. Is there a way to state the condition in double brackets without talking about C and W directly?
So it is independent of the homothety, right? And it's independent of your choice of basis, because all I'm asking is that it be in the field. So if you apply you do the SL2 action over here to your Z and W, which amounts to this, right? Then you're still going to be in the same field. So I don't know a way to write it down that maybe doesn't, I don't know, maybe somebody has a suggestion, but it is independent of what you want it to be independent of. Okay. Okay, so we have this map then we can think about going from the upper half plane to the lattices. And this is surjective because if you have any lattice, you can scale by homothety to make one of the entries 1, right? And so you can have something that has a 1 in the second coordinate right here. So this is surjective. And then what you want to know is what the kernel is. And so this is a computation, right? We want to take two images and ask when they might be homothetic, which means they give the same homothety class of lattices. And what that means, of course, is that there's some scaling factor, maybe a lambda.
So when you say kernel, you are referring to it being some kind of morphism?
Well, okay, I mean fiber over 0. Yeah. Yeah, that's fair. Okay, so we want to know, well, not even over 0, just what the fibers look like. Maybe I will say that. Right? So we just want to know when we end up ending up with the same lattice. And so this means that if they're the same lattice, so now I've scaled so that they're actually literally the same lattice, that means that there's just some change of basis that gets me from one to the other, right? So what this is telling me is that Z1 and 1 can be written somehow as alpha of lambda Z2 plus beta of lambda, and so on.
I
Yeah.
think on the first line, one of the two is 1.
Oh, let's put the 1 over here. Thank you. Is that better? Okay, so this just means it's a change of basis. Did I do? Oh, I'm hopeless. Okay. I think that's okay now. 2's on the right, 1's on the left. Okay. And so this just means that there's some sort of change of basis, and this is the element of PSL2Z. So what this is telling me is that Z2, as thinking of it as an element in the in the upper half plane or in the complex plane is just an image under PSL2Z of the other Z1. Okay? So this just tells you that what we're doing is we're quotienting out by the action of SL2. So that tells us that H quotiented out by this action is actually a bijection with lattices. And explicitly, it's that map. Okay? Okay, so that's just going to be useful for later. So I just wanted to make sure that we had that. So are there any questions? I didn't go in too much into the number theory side of it, but okay. Okay, so now let's turn to Apollonian circle packings. So I want to motivate Apollonian circle packings a little bit. So they're beautiful, right? And so everybody kind of enjoys playing with Apollonian circle packings. But I want to motivate that they're actually an extremely natural thing from the point of view of number theory. And that's from the point of view of continued fractions. So I want to make an analogy with what's going on last time. So we have Asmus Schmidt. I'm going to put the first name because there are very many Schmidts in the world. So he has an analog to the Ferry subdivision. Okay. And so on this side, let's remind ourselves what the Ferry subdivision looked like, right? One piece of it, so it was built out of these triangles, and each piece of it is sort of built iteratively by choosing the mediant. And then if you want to have the whole thing in the upper half plane with all of its bits and so on, right? Then what you do is you take the PSL2Z orbit of one of those triangles. Okay, so that's one way of thinking about that. And what it gets you is the continued fractions. It gets you the most natural way to describe the rational numbers and so on. And what Schmidt was interested in doing was doing this inside the complex plane instead of the real line. So you can do something analogous. So the real line is the boundary of the upper half plane, which is a hyperbolic plane, right? You can think of the complex plane as the boundary of a hyperbolic upper half space. And if you think about what these things are geodesics, right? And so it might be natural, and this was Schmidt's perspective, it might be natural to think about geodesic planes above the complex plane, which are just sort of forming these hemispheres, right? And somehow nesting those to develop an analog to the Ferry subdivision. So the idea was that you build things that look just like Descartes quadruples like this. And this is the fundamental piece, and you might visualize it as really like nested, bubbles sitting inside C, right? And now over here we have these rational numbers, these cusps. Those are, that's really the purpose of the structure on the left-hand side. And over here there are also important points. They're the tangency points, and there's 6 of them. And so in his view, that's the fundamental sort of unit that you should be using for the correct analog of a Ferry subdivision, at least from the point of view of the Gaussian integers. Okay? So over here we've got P over Q, and over here we're going to have Gaussian integers. All right? And you might do a different structure if you were working with a different number field. Okay? But the Gaussian integers were like a natural place to start. So then what you can do is there's sort of a most fundamental choice for these guys. So this has one point at infinity because those two horizontal lines are meeting at infinity there. And so what then you can do is take the PSL2 Z adjoint I orbit of this guy. So this is the real line. This is I, 0, 1, 1 plus I. Okay? And then that will get you sort of an analog to the Ferry tessellation. Now, one of the things he was doing, I'll just briefly point out, is there's always a dual arrangement that goes through the same tangency points and is 4 circles that are mutually tangent. Yeah, question?
When you do the PSL2Z adjoint Y orbit, do you just get the Apollonian gasket for that thing?
No, you get much more. I'm going to show you a picture in a second.
Okay.
Yeah. Okay. Yep.
PSL to ZI acting on the upper half plane?
Nope, this is acting on the complex plane. So this is in C hat, okay? Thought of as the boundary of an upper half space, which is a model of hyperbolic 3 space. And so these are the boundaries, circles are the boundaries of geodesic planes. So we're all moving up 1 dimension from the fairy case. Okay, so, right. Okay, so let, yep.
So in the case of like the fairy, just classical fairy sequence, you have a way to like organize the non-convection facets.
Yes.
What is the analog here, as in what, as in the circles that you have in here, how would the analog to say this circle comes first in the sequence?
Yeah, it does do the same thing for you. So basically, you know, these guys here might be the simplest. This is kind of like the analog to the unit interval in the fairy situation, right? These are the actual Gaussian integers. So they're the simplest. They have denominator 1 in some way. And then this guy has denominator 2 in the middle. And as you continue iterating this subdivision, you're going to generate the Gaussian rationals in order of complexity, in fact. So it is a way, it does have the same purpose.
So sort of just Euclidean size of the circle, right?
It's a little bit different. So let me pull up the picture. I might still have the slides from yesterday open. Okay, so let me pull over yesterday's slides. So if you iterate this, this is what you get. Okay, so you get this, this is the orbit of the real line under PSL2Z adjoint I, and actually you see exactly that configuration that I had up a second ago in the middle. So you've got the 2 lines. Whoops, I zoomed somehow, that was strange. So you've got the 2 lines in the middle, and then you've got these 2 circles, say, right, as the fundamental thing. So in fact, it's the same orbit, whether you start with just the real line or you start with that whole configuration. I'm not worrying about like hitting some stuff twice or whatever. Okay? And you can see inside here that then inside the circle, at the next iteration, you're going to have an Apollonian circle packing. You've got 3, say, tangent circles. You might choose those ones, because what you're doing is you can think of it, one way of thinking, building this thing, would be to take this circle and reflect it inside, and then take this line and reflect it inside, right? So if I go back to the notes, if I reflect inside this red circle here, I'm going to end up with this, okay? And so you build in like that. And you also do the Apollonian circle packing thing, which is that you're filling in the triangles as well. Okay? So Schmidt's I haven't explained how this accomplishes all of that, but that's what it does in practice. So it'll look like that, yeah.
Do the circles also have some meaning? Like your PSL to ZI or points there, right? So
No, it's the orbit of the real line. So all these circles are orbits, are the orbit of the line.
You can think of each circle as being associated to one element of the Bianchi group, one element of PSL2Z adjoint I. Yeah, but if you want to draw the picture for yourself, if you're doodling, right, then what you would do is what I was describing here. Yeah.
Is there some like interesting analog of Carey addition in this new setting, where you're sort of combining that point of tangency and
Yes, yeah. Yeah. So over here I've said you can do the median. You're asking about that, right?
Yeah.
Yeah. Yeah, I think you can build it that way as well. I forget the details, but I worked it out at one point. Yeah. Okay, so really I just wanted to, I'm going to go into all the details of everything eventually, but I just wanted to give that as a reason why Apollonian circle packings are actually a really natural thing to study from the point of view of number theory, besides just being cool, right? Yeah.
So if you look at the arcs in the fairy tales, are those or are they not the SLTZ orbit of the
No, so the SL2Z orbit of the real line is just the real line, right? It's not going to take you outside the real line. It's the SL2Z orbit of the imaginary axis. That's, yeah.
So in the fairy case,
Yeah.
say that the Schmidt arrangement is just the real line, or the Schmidt arrangement is the whole fairy?
The Schmidt arrangement is the rational numbers.
Okay.
It's the boundaries of that
Okay, so the
fairy tessellation. And so you're up a dimension and something different happens, right? Which is that these points here, which I'm thinking of as the important points, those are rational points. They're Gaussian rationals. But I'm really thinking of the whole circle as being part of the arrangement. So I'm actually adding in stuff that's not even rational because I've got something of higher dimension. But in the real line, you've just got points as the boundary, and so you just get the rational numbers, just the cusps of the. Okay, so the analogy here, just to be a little bit more explicit, so we've got the fairy subdivision on one side, and we've got the Schmidt on the other side. And by the way, I put Schmidt's paper up if anybody wants to take a look at it. So he had an earlier paper where he talks about the fairy, sort of the fairy addition and stuff like that you were asking about a second ago, but doesn't think about it as circles. And that has fairy in the title. And then he has one where he's talking about Diophantine approximation in the complex numbers, where he finally draws these pictures. So if we want to, say, approximate something in the reals by rationals, over here the Schmidt arrangement is really talking about approximating something in the complex numbers by something in the Gaussian rationals. So it's really to do with that particular field, unlike yesterday where I was doing all quadratics. So we have continued fractions, and they have their convergence, P over Q. And then you ask, what's the sort of analogy over here? And these tangency points are important. But we're up a dimension. And so not just the tangency points are important, but actually the circles are important as well. We have more room kind of for different levels. And so I would also say that the curvatures of the circles, the size of the circles themselves, is also sort of a piece of what's going on. Okay? And this is where you end up getting, well, that's where we end up asking questions about. I guess I should maybe more generally say that on this side, just, you've got the tangency points. You've got just a little bit more dimensional space, right? So you've got the tangency points, but then you've also got the circles. And at the same time, you also have an intermediate level in terms of the complexity of the picture. So if I go back to the picture for a sec, you've kind of got Apollonian circle packings sitting inside there, which are a part of what you do. And then you can also invert inside each circle and start doing an Apollonian circle packing in there, and then invert inside. And so you can kind of arrange the group in your mind as being like there's an Apollonian piece. So I'm going to describe that in detail. And then you can add the inversions and get the full Schmidt arrangement here. And so the group kind of breaks into an intermediate level as well, I'd say. And so that's why I think of the Apollonian circle packing as being kind of a piece of the picture. Just like the triangle is a piece of the fairy tessellation, here we have a circle, then we have an Apollonian circle packing, then we have the Schmidt arrangement. It's like 2 levels. Okay. All right, and I'll explain what I mean by a thin group, but it's a very small group in some sense inside the Bianchi group that generates the Apollonian packing. And so it has all kinds of interesting sort of challenges that don't exist for something like the Bianchi group. Okay, so that was just for motivation for why we want to study Apollonian circle packings. And now I'll start answering some of the questions. Yeah. So I don't think there's something over here. That's kind of like you've got in the fairy tessellation, you've got the triangles, which are kind of like the circles, and then you've got the endpoints. And on this side, you've got the circles and the tangency points, but you've also kind of got these units of Apollonian circle packings built out of circles, but aren't the full Schmidt arrangement yet. They're kind of between the structure that lies between. And so if you want to understand the full Schmidt arrangement, it makes sense to study the Apollonian circle packings as a piece of it to get started. So there really isn't something.
Is it reasonable to say that the very sort of, how do I say, the Schmidt arrangement for SL2Z, like you said earlier, is also really aligned with the rationals within it? So in other words, the Schmidt arrangement in general is like a bunch of circles with dots on them, dots are tendency points.
Yeah. Yeah, it's like a bunch of intervals in the real line, right? Like well, I want to say that the triangle has its endpoints. I would say the rationals are the Schmidt arrangement. That's the correct analog. I think that's what you're saying, right?
So in that case, you say the Schmidt arrangement in general is just the circles.
No, I want to include the circles. It's an arrangement of circles for me. But that just doesn't exist in the fairy one because you just have endpoints. That's your circle. Your circle is a S0. The fairy case is one dimension down, so yeah, we're defining it differently. But the correct analog would be the image of like the point 0. Because it's one dimension down, yeah.
Yeah, one other weird thing is that the Schmidt case is not nearly as tree-like.
Yeah.
Somehow, because you have like these.
Yeah. It's not a tree anymore.
You don't have the same kind of strict nesting.
Yep.
In a way.
Yeah, exactly.
That's another thing.
Yeah, and that adds a lot of complication.
Yeah, SL2Z is not virtually free. Right?
Yeah, and over here too, when you do 3 circles inside your big circle, you haven't captured the entire interior. Yeah. So there's a bunch of ways in which it's much more complicated.
Maybe one thing, like there might be, if you think about putting intervals of size 1 over q squared around each rational, then you either have containment or they touch, right? Like you have another, and so if you want to think of the interior of the circles in the Schmidt arrangement case, then the interior of the S0s is these intervals, right? Like is one way maybe you could think about it.
Yeah, but they completely cover the real line. Yeah.
So the base circle in you said equals 0 infinity. The circle 2 point.
Yeah, it's an S0 with just 2 points. Yeah. Okay. So Apollonian circle packings. Okay, so I'm going to start with the geometric aspects before getting to the number theory. And so on the first day, I showed you how to build an Apollonian circle packing, right? You start with any 3 circles, and here you have some free choice how to arrange them, as long as they're tangent to one another, okay? And then you just keep building circles, always disjoint interiors. So what I can do is I can add circles into each of the triangular regions, which is left over, and keep trying to fill up space, okay? And I wanted to show you, so I have notes online, and I thought I should mention that the notes, they have exercises in them, so you'll find exercises in there. This is Schmidt's original paper, by the way. So this is a screenshot, and he had these regions. This is, over here, this is a triangular region, because it's joined up at infinity, right? This is a triangle in which he's putting a circle. Okay, so that's the filling a triangle with a circle. And then you have, if you have, yeah, okay. I'm not sure exactly what I was going to say. But anyway, so he's describing in this picture here, he wants to do continued fractions. And so he's describing a process, just like you go down through the fairy the Ferry tessellation to track your continued fraction. He's describing a process here whereby you go down and you enter a region, and if it's a triangle, then you add an extra triangle inside, and if it's a circle, then you fill 3 circles inside it to keep going like an Apollonian circle packing. So he has, and you've already got these, you're tracking your points, so you know which 3 circles to add and so on. So, so basically, he has this iterative process, but he never drew the picture. This was the only picture in the paper. And so he never, I mean, as far as I know, he may not even know what it looked like, how beautiful it actually is when you ask the computer to continue this process. So he just described the process. And in the notes, I have, so there's another picture, just a detail of what it looks like. And I have a few Apollonian circle packings to share. So this one on the right there is drawn by Kat Sandin, who did some work on Apollonian circle packings when she was a student at Princeton. And on the left is a packing generated by the software of my postdoc, James Rickards. He has this very user-friendly software if you've got PeriGP on your computer. And you can actually zoom in on this packing, and it's a PDF. So you can enjoy all of those little curvatures, and you can set it to as many curvatures as you're willing to have your computer do. So it's just very enjoyable. So if you want to enjoy some Apollonian circle packings, you can play with that.
Do the pictures mean anything?
Do the pictures mean anything?
Like the colors, the people.
The people? No, I think it's just an Apollonian fever dream. But it became, that one with whatever curvatures it has became known as the people packing. And if you go to Elena, there's a paper of Elena Fuchs and Kat Sandin. They have the bug eye packing, there's a drawing, and the coins packing. Okay, so we saw before that if you have a Descartes quadruple, so on the first day, that you get this relationship. Okay, where the curvatures are 1 over the radius. And then from this, if you have A, B, and C already chosen, then D and D prime have to satisfy this relationship, which means that if you have A, B, C, and D already integers, then you get all integers. And so that's where we get these, the number theory interest. So if we want to study the fractal, we want to understand what group of symmetries it has. So we have the Apollonian group. And this is generated, so basically this form over here, so let me reorganize this and say Q is that form, okay? So the Descartes form says Q equals 0. So as a form, a quadratic form in 4 variables, this guy has signature 3,1, which tells us that Minkowski space is going to appear again. So we can talk about the orthogonal group preserving that form of signature 3,1. And that would be 4 by 4 matrices preserving Q, okay? And this will act on the set of Descartes quadruples. So when I say Descartes quadruple, sometimes I mean the 4 curvatures and sometimes I mean the 4 circles, and you'll just forgive me for that, okay? And so the fundamental generators that I want to use are the ones that come from the way that we generated the packing in the first place. If I have a Descartes quadruple and I've chosen 1 circle, then I can choose the other solution to Apollonius's problem in terms of the 3 black circles. Okay, so this is called a swap. And the idea is that you have 4 choices. If you've got a Descartes quadruple to start with, you have 4 choices for a swap. And I can write down the matrix very explicitly. So if I want to swap the first curvature, so here I'm going to take S1, and if I'm writing it so that I'm going to act on, I'm not sure that I made the right choice here, but I'm going to act on row vectors, okay? So this is going to swap out A for A prime, all right? And because we have this equation right here, it's a linear action, so I can write down exactly what the matrix looks like. I don't know why I drew a funny bracket for my matrix. So my new A is going to look like that linear combination of the previous stuff, okay, just from this equation right here. And then the other things are preserved, all right? And so you have an analogous swap for each of the other circles in your quadruple. Okay. So this Apollonian group, so we'll call this A, curly A, okay? It's going to look like generated by these things. These are each inversions. They have order 2, and there's no other relations. So the actual presentation is just this. It's the free product of just Z mod 2Z. There's no further relations. So that means that if you want to draw a Cayley graph of this, it really does look like a tree. Okay, so the Apollonian circle packing at least has this treeness that we lose in the Schmidt arrangement. And this is what's called a thin group. So what this means is that it has infinite index inside the larger group, the orthogonal group. So it really is small in this sense. But at the same time, it's Zariski dense. I'll tell you what that means. So what this means is that basically it can't be cut out by polynomial equations. So if, for example, you have some polynomial which vanishes in the entries of your matrix for every matrix in the Apollonian group, then it's actually going to vanish on the whole orthogonal group. Okay, so this means that there's no way to detect if you're inside the Apollonian group by some polynomial test on your entries. Okay? And that's important because it means that all of the sort of algebraic geometry things that you might want to do, well, it's not an algebraic geometry object. Okay? So OQ is, if you want to cut that out of, I don't know, 4x4 matrices or something, you check that they're orthogonal, right? Yeah.
In practice, doesn't it just mean that it doesn't preserve a hyperbolic plane or a plane at infinity or some other thing like that? Just for a rough and ready way of saying what the Zariski dense means geometrically.
Well, I guess if you were to preserve, if you had a fixed point in mind, that would be an algebraic condition, right?
Sure, yeah, that's
yeah,
what I mean. But
that's what you mean.
one thing that could go wrong.
Yeah, I'm not sure. I mean, something more higher degree is also not going to work. So it's not just that, right? Like it's polynomial.
Yeah, that's not, yeah.
Does it make sense?
Yeah, I don't think that could happen. But anyway, yeah, never mind. I just wanted to sort of understand it like completely.
That's certainly, yeah, it certainly is the case that it won't do that. I'm not sure if that's equivalent.
Yeah.
Yeah.
Okay.
Yeah. Okay, and so that's sort of what makes this such an interesting group from the perspective of algebraic geometry and arithmetic geometry and number theory, is that we have lost the tools that we would like to have, okay? And so we want to study questions about the orbits of this group, but we don't have the usual tools, and we have to invent other tools, and that's what makes it an appealing problem to number theorists. Okay, so we also have, where am I for time anyway? Another 10 minutes, okay. So we also have the super Apollonian group that this sits inside, and that's what gives the full Schmidt arrangement. And we can build that, we just have to add a little bit more. So here's my circle packing. And now what I want to do is I want to invert into one of the circles. So if I invert this quadruple, so remember I'm acting on quadruples. Up here I was acting on them by swaps. Now I'm going to act on them by inversions. And what that means is I'm just going to invert the picture you have outside, circle inversion here, to get a quadruple inside. So I'm fixing one circle and changing 3 circles now. All right. And maybe it's a fun exercise to write down the matrices for that. You can write them down. But this super Apollonian group, let's call it SA, the presentation now, you have the original Apollonian group. And then these swaps I'll write like that. And, well, maybe I'll write it as a presentation, right? We've got some relationships. So we know that the swaps, and in fact also the inversions, are order 2. Okay? And then we also have, it's really not a tree, we also have that if you combine a swap and an inversion, oops, why did I do that? Then you can commute them when they're different. Okay? You can kind of imagine that geometrically if you like. Okay, and so that's what the super Apollonian group looks like. And so let me show you a picture again of the Schmidt arrangement, but generated with the super Apollonian group. So this one. So this is the length 5 words in those generators. So this gives you a bit of a sense of generating the group from those generators, what the Cayley graph might look like. Okay? And so you can see that there's areas where there's more density as you do this. So these are in normal form because I said that there's some relations, right? So that means I've eliminated any squares and I've made a choice if I have a swap and an inversion of which one to do first. Okay? And so you can actually use this to define a dynamical system and define geodesic continued fractions as you move down through this. So that actually tells you what the invariant density ought to be when you try to do that. So I actually have a picture of it. So my graduate student was interested in this, and you can kind of see this picture here is a picture just computationally what the invariant density looks like. And it sort of matches the density of the words there. So I'm not going to go down this path, but... So, say what? Sorry? Ah, you want to see this again? Yep. The swaps and inversions will commute when they're not on the same circle. So not everything commutes. Yeah, so because these are the same here, normal form means that I'm going to pick, oops, I forgot I'm not in the, so normal form here means that I'm going to pick from amongst these two when I have things that commute. So there's a little bit of commuting, and I'm going to make a choice whenever I have the option. So it's kind of, the Cayley graph kind of looks like, kind of tree-like, but there's these diamonds.
Okay, you don't need to choose because they commute, so it's the same length, but since the length...
Yeah, that's true. The length is invariant. So yeah, I don't need, for the purpose of this picture, I could, yeah, absolutely, yeah. Yeah, but if you wanted to find a map or something, you should make a choice, yeah.
So this is an invariant density for the action of this group on the boundary. That's or for the dynamical system that you're going to get.
For the dynamical system that you would set up to move to the root in the Cayley tree, like,
Okay.
yeah. Yeah, I think I'm supposed to stop actually now, right? So let's just take questions. Thank you.